Hi everyone, so today we're going to look at how to solve this wave equation. This is one-dimensional wave equation given by this equation here, the second partial derivative with respect to x and t. Now we want to show the solution to this wave equation, which is also known as the vibration of a string on infinite region. Okay, so we're given the initial condition and also the derivative of the initial condition. This is the initial velocity here, which is gx. Okay, so we want to find when t greater than 0 and x from minus infinity to infinity. So we want to solve this using Fourier Transform because we have infinite region here. So let's use Fourier Transform. So if you look at the first step that we need to do is to take the Fourier Transform of the wave equation. So the Fourier transform the variable x, unlikely the Laplace transform the variable t. Okay, so what we do here, this one remain the same, where we have dt squared, and what we have here, we have the hat for Fourier transform, and my x will become, this is the transformation you do. Okay, so let me just put it here. Laplace transform of fx will give you f hat omega. So my variable x changed to omega. Unlikely, this is a Fourier transform. Unlikely, the Laplace transform of t gives you big F s. So t become s. For Fourier transform, x become omega. Okay, so now the transform of this f here will be, this is the derivatives formula that we use, where you have u hat, and we have omega t. Okay, remember x will become t here. Now simplifying this, or in another way, I can write as omega t equals to I squared is negative 1 omega t. Okay, so this looks like a second order homogeneous equation, where I can write this as plus c squared omega squared u hat omega t equals to 0. So in other word, I won't write it, but in other word, let me show you. This looks like exactly in this form. Okay, so the characteristic equation here is m squared equals to negative c squared omega squared, which is m will be, we have a complex root. Therefore, my solution to this u hat is given by a cos c omega plus b sine c omega. Okay, now what we do, we want to find this constant a and b. So we apply the first initial condition. So the initial condition is given where u x0 equals to f x. So I'm taking the Fourier transform for this initial condition. Fourier transform of fx. Like I said, This will become u at, x will become omega 0. Now this one will become f hat omega. So look at this equation here. What happened here when t is 0? Okay, when t is 0 here, we have f hat omega equals to, oh, I forgot to put t in this equation, so this is my bad. So we have c omega t, c omega t. Okay, so when t is 0, sine 0 is 0, so that lets me cos 0 is 1, so this is equals to a. Okay, so my new equation will be a become half hat omega cos c omega t plus b sine c omega t. Okay, now we have another initial condition. The second condition said that u hat, derivative of u hat x0, sorry. Let's do it one at a time so that you won't get confused. So this is the given x0 equals to gx. Okay, now similarly take the transform, the Fourier transform of this derivative. Give you the Fourier transform of g. Now the Fourier transform is simply u hat derivative omega 0 equals to g hat omega. Okay, which means we have to take the derivative of this equation. Let's call this star. Now the derivative of star gives you ut hat omega t equals to, now you're taking derivative with respect to time, so whatever omega will remain as a constant. Now taking this one, I have negative c omega sine c omega t. This is for this one. Now for this one we have plus b cos c omega t, and you have c omega. Okay, now what you do when t equals to 0, when t is 0, because we're taking this condition here, so I have g hat omega equals to f hat omega. Okay, what happened here when sine 0 is 0? Cos 0 plus b cos 0 is 1, so I have c omega. Okay, this is 1 when t is 0. Okay, that will leave me b equals to g hat omega over c omega. Okay, sounds good. So now our new equation will be w hat omega t equals to f hat omega. Okay, and then we have cos c omega t plus b, which is g hat omega over c omega sine c omega t. Okay, we are nearly there. Now all we have to do is we want to find uxt. Then we got to have Fourier inverse transform of this equation here. Okay, so by the linearity property, I can take this inverse, Fourier inverse of g hat omega over c omega sine c omega t. Okay, so what happened here now? So inverse of this, I'll write it in a blue, inverse of this is u x t. Now this term, there is a Laplace table for this, so let's look at this one here. So we have from the table, from the Fourier table, I get confusing with Laplace and Fourier, but just bear with me. From the Fourier table, we know that the inverse of 2f hat omega cos omega c is given by f of x plus c plus a function of x minus c. Okay, now I'm simplifying this, so what we have, Fourier inverse of f hat omega cos c omega t. Okay, if you look at carefully from there, so we have this 2, bring it over here, and then we have x plus c, right? But we have omega, so ours will be omega t. Okay, so this is based on here, x plus c, x minus omega. Okay, so we have ct. Okay, omega remain, omega, and then c. So we have x plus ct plus f x minus ct. Okay, so that's what we obtain for this the Fourier inverse involving function and cos. So, but now we're gonna look at this part here. Okay, so the Fourier transform, Fourier inverse transform of g hat omega over c omega. Now I want to write it in a different way, such as c sine c omega t over omega. Okay, so this is what we want to find next. There is a table for sine, okay, sine omega, where we can use the the Heaviside function definition here, where from the table, okay, let me just this can be used as a convolution theorem. So we look at here, we have Fourier inverse of g hat omega over c and Fourier inverse of sine c omega t over omega. Now you can find this in the table. Okay, so I'm just going to write it here, maybe in a red letter. So the Fourier inverse of 2 sine omega a over omega is given by h x plus a minus h x minus a. Okay, so so if you look at this equation here, so this one, I'm writing it right again, based on this property. Now this c here, I can bring it outside. Okay, so I have 1 over c Fourier inverse of g hat omega. Now this f, this whole thing here, by referring to this one, we have where ct, so my a will be ct and half, so I have half h x plus, okay, x plus ct minus h x minus ct. Okay, continuing what we have here, again I can take 1 over 2 outside to see. So I have the inverse of g hat omega, and also this whole thing I can denote it as h. Okay, h hat. So we haven't transformed this yet, so I'm gonna call it as the Fourier inverse of multiply with or whatever h hat omega. Okay, now we need to know that this is, you can use convolution theorem. Now the convolution theorem says that the Fourier of g times of x, okay, is given by integration from minus infinity to infinity g. Okay, we have g x minus psi and f psi d psi. Okay, this is the definition. Now whatever we obtain here, okay, I'm gonna change it. Okay, look here. So we have half 2c. Now by the convolution theorem, okay, so I have minus infinity to infinity. My g here will be x minus psi. Okay, so I have g x minus psi, and then everything inside here will be, my x will become psi, so I have h. So maybe put like this, h psi plus ct minus h psi minus ct, what is it, d psi. Okay, or I can simplify this by breaking or splitting these two function here. We have x minus psi h psi plus ct d psi minus, okay, this thing and multiply with this, minus infinity to infinity g x minus psi h psi minus ct d psi. Okay, now the other thing we want to look at is, okay, so this graph here. So if I'm about to sketch this graph here, so if this is, I want to look at negative ct, from here this is my h psi plus ct here, and the other thing will be here ct. So this will be my h psi minus ct. Okay, now all I want is, okay, so all I want is from negative ct to ct. Now this part, the integration part for this one. So I can write this as 1 over 2c from minus ct, so you have minus ct to infinity dx minus psi d psi, okay, minus 1 over 2c from ct to infinity, so we have ct to infinity gx minus psi d psi. Okay, now you can combine them because all you want is from minus ct to ct gx x minus psi d psi. Okay, now what this tells you, here, okay, it's not yet done. So this is what we have obtained, but we're going to use more transformation. Okay, F inverse of G hat omega over C omega sine C omega t is given by 1 over 2c for minus ct to ct g x minus psi d psi. Now let z equals to x minus psi such that psi will be x minus z. So what we have, d psi over dz will be minus dz. Okay, I'm going to transform this to z. And then when psi is ct, so what happened to my z? Ct, this is psi, equals to x minus z. That gives you z equals to x minus ct. Now similarly, if psi is negative ct, I have negative ct equals to x minus z. Now this will gives me z equals to x plus ct. Okay, having all this transformation, I can write the Fourier inverse of g hat omega over c sine c omega t over omega is given by 1 over 2c. Now negative ct, change it to z here, so I have x minus, okay, negative ct is, which is x minus z, my z is, okay, so we have here x minus ct, and this is x plus ct g z, because x minus psi is z, and this is negative dz. Okay, remember we have made the transformation. So if you look at here, this negative ct is my x minus z. Okay, z, which is go back to here. Okay, now with the negative sign here, you swap. Okay, these two function has been changed because I have a negative set here. So then, okay, so this is what we have obtained. This is what we have obtained for the Fourier inverse of this. So now let's recall back whatever we want to find. So we have obtained the solution omega t equals to f hat omega cos c omega t plus g hat omega over c sine c omega t over omega. Now taking the Fourier inverse of the above function gives you plus Fourier inverse of g hat omega over c sine c omega t over omega. Okay, now we have obtained earlier on where this is uxt, the inverse of this. Now the inverse of this is given by half. We have obtained fx minus ct plus fx plus ct. Now the inverse of this, which you have obtained just now, which is 1 over 2c plus 1 over 2c integrate x minus ct x plus ct dz dz. Okay, so this is the solution for the wave equation on an infinite interval. Now, if you look at that, if let's say my g is 0, so if my gx is 0, that means like we don't have this whole term because this exists from the second initial condition. So you will have an equation involving half a function of x minus ct x plus ct. Now this is also called the traveling wave. Okay, this is known as the traveling wave involving where we have the positive and negative function here. Okay, so that's all. So I'll see you in my next video. Bye.